Muy bien, buenos días a todas, buenos días a todos. Gracias por estar aquí. Vamos a dar inicio a la primera charla de esta mañana. Maurice, can you hear me?
I can hear you.
Okay, thank you very much for being here. We are really honored to have you here. We are happy that you are going to share your story today with us. If you don't mind, I'm going to introduce you in Spanish. Is that okay?
That's okay.
Okay, thank you. El profesor Maurice Cox es un miembro emérito del NPL, el National Physical Laboratory del Reino Unido, que es, por así decirlo, como el CENAM allá, y está en el Departamento de Ciencia de Datos. Tiene una licenciatura en Matemáticas Aplicadas en la City University de Londres y un doctorado en Análisis Numérico, particularmente funciones de spline, por la City University. Ha trabajado en la NPL desde 1968 y actualmente es consultor con compañías que tienen intereses de investigación en matemáticas y en modelación estadística, cuantificación de incertidumbre, desarrollo de algoritmos y análisis numérico. Le interesan los aspectos genéricos de la cuantificación de incertidumbre y métodos de evaluación y de comparación interlaboratorio. Tiene mucha experiencia en aplicar estos enfoques a diversos campos del conocimiento. También ha hecho contribuciones mayores a los suplementos de la Guía para la Expresión de la Incertidumbre, la GUM, y guías relacionadas, porque ha trabajado en el Comité Conjunto para las Guías de Metrología, JCGM. También fue líder recientemente de un proyecto europeo, EMUE, para producir muchos ejemplos ya desarrollados de cuantificación de incertidumbre. Los ejemplos incluyen muchos sectores: energía, medio ambiente, calidad de vida, industria y sociedad, y ha apoyado el trabajo del Comité Conjunto para las Guías de Metrología en más de 10 comités de estándares. Hay una serie de ejemplos, si ustedes pueden ver su semblanza en la página del evento, podrán accesarlo a través de una liga. Es presidente de varios y miembro de varios comités nacionales e internacionales, incluyendo el British Standards Committee y también los comités para el desarrollo de métodos de medidas y demás. También de la ISO y de métodos de apoyo para evaluación de incertidumbre de medición. Y también es director del grupo asesor para medidas de incertidumbres del Buró Internacional de Pesas y Medidas. Como pueden darse cuenta, es una trayectoria impresionante. Y también es miembro fundador del Instituto de Matemáticas y sus aplicaciones, y es un matemático certificado y socio emérito de la Royal Statistical Society, de la Sociedad Estadística del Reino Unido. Y actualmente es un profesor invitado en matemáticas computacionales en la Universidad de Kingston, en el Reino Unido. Ha publicado más de 300 artículos y reportes. Pues con eso se dan cuenta del calibre del presentador que tenemos hoy. Espero que disfruten mucho su charla. And Maurice, we are ready. Whenever you want to start, it's okay. Thank you.
Yes, that's fine. Thank you, Eduardo and Jesus, for giving me the opportunity to speak at this conference. The last time I was in Mexico was in 2018, where I was asked to give 3 lectures, 2 on the gum and 1 on Bayesian methods. This time, sadly for me, I'm speaking to you only online, but it's better, certainly better than nothing. I'm very happy to be with you again. Unfortunately, my Spanish is not good enough to speak it as a presentation, so I'll be speaking in English, and I'll try to speak as clearly as possible. Okay, I'm speaking on the subject given on the screen there. Over 30 years of the GUM, and I've been involved in GUM work. The committee that supervises the GUM is the Joint Committee for Guides in Metrology, and I'm a founder member of that committee, which started in the year 2000. I've attended all 51 meetings so far of that committee. Okay, the coverage of my talk is as follows. The GUM, the Guide to the Expression of Uncertainty in Measurement, is first published in 1993. I think most of you are aware of the GUM, and it's the most authoritative document internationally available on measurement uncertainty. Over recent times, although it's been available for 30 years, over recent times it's evolved into a suite of guides for uncertainty quantification. The legacy GUM, the original GUM, with sister documents covering an introduction, modeling, Monte Carlo methods, multivariate problems, and conformity assessment. It's still evolving, with new guides being developed as we speak. I want to talk about the GUM suite, the past, the present, and the future, emphasizing an aspect which isn't concentrated on enough, in my opinion, the validity, the fitness for purpose of the GUM and its sister documents. I'm going to indicate principles and tools I've found valuable in many applications. I'm concerned with the propagation of estimates as well as uncertainties. I like working with probability distributions, which have a great amount to give in this area. The Joint Committee for Guides and Metrology, as I say, supervises the GUM work. It has 8 powerful member organizations, including the BIPM, the International Standards Organization, and I've listed them there. The terms of reference are to develop and maintain guidance documents, the GUM and the VIM, the International Vocabulary on Metrology, addressing the general metrology needs of the community, and to arrange for the dissemination of these guides. To promote the adoption and implementation of the result of its work, and to provide advice relating to its guidance documents. In general, there are hundreds of thousands of downloads per year of the documents in the GUM suite. So there's still a lot of interest in the GUM and its sister documents. Talking about past, present, and future. In the past, the 1993 GUM gave a way of assigning uncertainties to model inputs based on the statistical analysis of repeated observations, type A, non-statistical information, such as instrument resolution and bias and so on, and expert judgment, type B, correlation effects from various sources, an aspect that's sometimes overlooked, type A or B. It gave rules for propagating uncertainty through a measurement model and constructing coverage intervals for the measure and the quantity intended to be measured. The GUM was eagerly grasped by the community, and it's to be found in working procedures, software, and many standards and guides. The centerpiece of the GUM work is the measurement model, which is a relationship y equals f of x between known quantities x and the quantities y we wish to know about. And a simple diagram of a measurement model is given here with 3 input quantities and 1 output quantity. There may be many output quantities. The function f may be mathematical or algorithmic. It may be real or complex. It may be explicit or implicit. And it may be also y, univariate or multivariate. A simple example of an explicit model is the volume V of a cylinder, V given by the formula in the center of the screen there, where the length of this cylinder is L and the diameter is D. A simple implicit model is one where we can't solve analytically or in closed form for the output quantity given the input quantities. I give a simple example here of the shell thickness of T of microscopic spherical particles, where A and B are measurement models, and the equation, the model is given at the bottom of the screen, the right, and it's impossible, as I say, to solve for T explicitly in terms of the other quantities. We want to find an estimate, little y, of the measurand y and its associated standard uncertainty. The legacy gum, the original gum, gives formulae for y and uy. In the univariate case, we have input estimates, little x, and standard uncertainties, u of x. When the x's are dependent, we have an input covariance matrix, and the document GUM 8, also known as JCGM 102, gives the multivariate case in some detail. The estimate of y is given by the plug-in principle. In other words, we plug into the measurement model the input estimates and compute the output estimate by that means. The standard uncertainty is given by the law of propagation of uncertainty. There's a formula for the independent case. I'm going to return to that formula later. Present. Over recent years, the JCGM has published 3 documents. 2 are available already, and 1 is imminent. GUM 1 is a completely revised introduction to the GUM suite and measurement uncertainty. GUM 6, in my opinion, one of the most valuable guides in the GUM suite, is concerned with developing and using measurement models. I said the measurement model is the centerpiece of the GUM work, and so developing and using measurement models is essential. We consider 5 steps. 1, specify the measurand. 2, model the measurement principle, a basic model, usually based on the physics or the chemistry or the biology of the situation. 3, identify effects involved in the measurement, like resolution and bias. Extend the basic model to account for these effects. 5, assess the resulting measurement model for adequacy. And GUM 5 is a document well on the way, the examples document, and I'll speak about that later. Here for the record, I presume a copy of these slides will be made available to you, is the status of the documents in the GUM suite. They're all freely downloadable from the address given at the top of the screen. The ones in the status column having a blank against them are available now. A number of documents are under development, some near completion. The one nearest completion is GUM 5, the examples document. That's imminent. And the other documents are underway. GUM 6 on modeling contains many inline examples, we call them. They're not fully worked examples, but they're one-page examples, that sort of thing. There's an example of a SIR model. If you're unfamiliar with the SIR model, that stands for Susceptible, Infected, and Recovered model, talking about infections. It's governed by 3 simultaneous differential equations for, in this case, this example, for influenza infection. We're given data indicated by the red dots on the left-hand diagram, and we fit the SIR model to that data by solving these differential equations and matching the solution to the data. You see that that model fits rather well to the data. The blue dots indicate the model values corresponding to the observed values. On the right-hand side, it depicts a probability density function, probability distribution for the reproduction number, which is one of the parameters in the SIR model, and it gives an indication of the likelihood or the frequency of the infection spreading. R0 equals 2.4. That's the expected value. It means that you're 2.4 times as likely to come to infection to increase. Such models, by the way, have been used in the COVID pandemic and with mixed success. Sum 5, the examples document. The JCGM sent out to the examples document an advanced draft of the examples document to the member organizations and to the National Metrology Institutes. It's being reviewed at the moment, and we're starting to receive comments, many comments from the member organizations and the National Metrology Institutes. There are 16 examples, fully worked examples, well over 100 pages in the document, but it's by theme, and users can be expected to search for the document to see the theme closest to their interest. We expect publication late this year or possibly early next year. The work is strongly based on a European project, Project EMU, which I led. The project was set up explicitly to produce documents to support the JCGM and various other committees. It gives examples, but also elaboration of the principles in the GUM suite. And I think I'll mention it briefly. The EMU project, which ran recently, finished 4 years ago, it promoted the harmonized evaluation measurement uncertainty. It was accomplished by providing new or improved examples to JCGM, International Standards Committees, and other bodies. It intended to improve the use by these bodies of accepted uncertainty principles. The important thing is that many examples are in a form that can be readily adapted to other areas. And the compendium, over 300 pages, is available, can be downloaded. The future. I want to mention 4 items: validity or fitness for purpose, the law of propagation of uncertainty, coverage intervals, computing derivatives, least squares problems, and consensus values, concentrating on key comparisons. I could have entitled this talk Obtaining Valid Uncertainties. Many guides, if we look in the GUM, many guides use phrases such as, it's usually the case that, it is normally the case that. Users reading that assume, rightly or wrongly, that such provisions of the document are correct for them. They might be wrong, of course. They might be using the GUM or the sister documents in circumstances where it's somewhat inapplicable. But what direction should we take those users when their problems don't fall into a proper category? So it's an interest in mine. My background is in numerical analysis and error propagation. I have considerable interest in making these guides more valid and fit for purpose. And I'm encouraging the JCGM to adopt this view. And I'm having some success. An even better subtitle will be Obtaining Valid Measurement Results, not just obtaining valid uncertainties, because at the end of the day, we want to provide an estimate of the measurand and the standard uncertainty or covariance matrix associated with that measure. Validity here applies to the mathematical or statistical problem we're solving. That's our model of reality. We have a basic model based on the chemistry or physics and so on, and we have a modified model taking account of metrological factors. And we present that mathematically or in the form of an algorithm. It's that problem we can apply validity to. And so we need a clear and unambiguous specification, analytical or numerical, and we're after that solution. Of course, most solution processes have imperfections. And so that adds to the difficulty of saying whether a process is valid or not. In my opinion, the users of the GUM suite have a right to expect a solution for that problem that is not appreciably marred by any further errors due to the imperfections of the data. Many solution methods introduce errors, and they without giving an indication of the size of those errors. And that's very unfortunate, because I've seen many examples in practice where users take a very small sample, for instance, because they work in a testing laboratory. Testing might be destructive, testing might be expensive, and so on. So they don't have an opportunity to take a small sample. If they're using large sample theory, large sample methods, they're likely to get an invalid solution. The law of propagation of uncertainty, I mentioned it already. The formula at the top is the basic formula, giving the variance of associated with the estimate, where we evaluate partial derivatives at the estimates to the inputs. There is a high order law of propagation of uncertainty formula, and I give it for uncorrelated, normally distributed input quantities in the middle of the screen. So we're getting complicated now. There's no counterpart expression given in the GUM for the estimate of the measure N. It's not the plug-in estimate that is given in the GUM, it's something else. It's the expression I've called Y2 near the bottom of the screen, which is the plug-in estimate plus an additional term which depends upon the input uncertainties. And that's very important, because if we have a highly nonlinear problem, that term can be appreciable. It can also be appreciable when the input uncertainties are large. It's getting complicated, and it's often easier to apply Monte Carlo. And we're pushing users to apply Monte Carlo if they doubt the LPU for their problems. Confidence, coverage, credibility intervals, we have all sorts of names depending whether you're a frequentist or a Bayesian or whatever. The law of propagation of uncertainty is exact for a linear model. That's the only occasion where it is generally exact. So to obtain a confidence interval, when we have type A inputs, when the inputs are defined in terms of repeated observations, there's a formula given in the GUM, in the legacy GUM, called the Welch-Satterthwaite formula, or the Welch-Satterthwaite approximation. The formula I've given on the screen here. U1 and U2 are standard uncertainties associated with two inputs for the sake of argument here. U1 and U2 are the degrees of freedom associated with these inputs, equal to, in the simple case, equal to 1 less than sample size. And this formula enables you to find the standard uncertainty associated with the output Y, and it produces a new F and effective degrees of freedom. and it approximates the output probability distribution by a student's t-distribution, which it isn't, and so it's an approximation to the distribution for the output. It's used routinely by metrologists, but the PDF so provided can be a poor representation of the true PDF. If we compare the solution according to the GUM, using Work-Satterthwaite formula, it compares unfavorably with the Monte Carlo solution, which the GUM regards as a reference solution, a gold standard solution, if you like, for the problem. And I've submitted a paper with my colleague, Tony O'Hagan, from Sheffield University, about how bad the Work-Satterthwaite formula can be and circumstances when it is likely to work well for you, and what to do about it if it doesn't work well. Simple measurement model, y equals x1 plus x2. You can't get much simpler than that, with two type A normal inputs, both with sample size of 3. The Work-Satterthwaite coverage gave 87% compared with the expected 95%. The expanded uncertainties associated with the solution, 3.9 given by Work-Satterthwaite, the true solution 6.5. So we're getting a long way from the truth here. You might say the sample size is small. I agree, it is small. But even for sample sizes 4 and 5, you can see appreciable differences from the reference solution. The worst case I've encountered where both sample sizes are 2 gives Work-Satterthwaite coverage of 80%, and the expanded uncertainty is a quarter of what it should be. That's why I say any cases of doubt, use Monte Carlo. Another thing I think I recognize as being difficult for a number of practitioners is computing derivatives, which we need when we're applying the law of propagation of uncertainty. A simple to use method will be appealing, especially if it can be applied to a mathematical function or an algorithm. Such a method is a complex step method. It's been around a long time. It was invented by Linus and Moeller in 1955, but it wasn't prominent in those days. But with the coming of the legacy GUM in 1993, it started to become more used in that area. I'm a great user of this method, which I should describe briefly, and it's a very simple idea. Derivatives can be approximated by finite differences. Difference between neighboring function values divided by the distance between the arguments of those function values. And that we have a real increment in computing those function values. What the complex step method uses is an imaginary increment. And so we take each quantity in turn, each variable in turn, we add a small imaginary increment to it and base our calculations upon that. And this increment can be 1 times 10 to the minus 100 times the imaginary unit, which we can't do with finite differences, because if we use such a small increment, the function values will appear identical. A little bit of complex variable work. The complex step method applies when the real types in a computation are replaced by complex types. Many computer languages such as MATLAB, Python, R, and so on support complex arithmetic. So we replace the real types in our calculation by complex types and go from there. Using the Taylor expansion of a function, as used in the GUM, but they for real quantities, of course, there. Using the Taylor expansion of a function of a complex variable, well, we can, at the bottom of the screen, you see the real part denoted by the script R, gives us a method of finding the real value, and the complex part gives a method of finding the first derivative. And so it works, and because we can choose h to be minute, it tends to give these values comparable to full machine precision. And so we have no difficulty with errors due to finite differences. A very simple example. Suppose we want to compute the derivative at x equals 1 of the function given on the screen there. 1 plus x times 1 plus 2x divided by 1 plus 3x times 1 plus 4x. I've worked with many functions, and this is a relatively simple one. An implementation in MATLAB, we set h, the increment, to be 1 times 10 to the minus 100. We set x, because we want the derivative at x equals 1, to be 1 plus the square root of minus 1 times h. We then compute f using the formula. We then take df by dx as the imaginary part of f divided by h. The real part of f is the real part of the complex f given in the above expression. The exact value in this case is minus 23 over 200, which the above code delivers correct to one binary digit of full machine precision. Now, I and many others have applied it to a number of problems. I've applied it recently to jet engine thrust, which was a complicated model involving many components, many input quantities, many output quantities. And we use a simple software harness rather than writing out a code such as this every time. The next thing, we're producing a least squares guide, as I mentioned earlier. And I'm surprised we haven't done this before, but under a lot of pressure from colleagues, we're starting to produce that guide, because least squares problems abound in metrology, adjustment of fundamental constants, key comparison data evaluation, fitting of models to identify physical parameters, calibration, the list goes on. Admittedly, the GUM suite does not consider least squares, at least directly, although it gives examples. GUM 10, which is the document concerned with least squares, which is under development, considers least squares problems in terms of a measurement model. I mentioned before, a measurement model is central to the spirit of the GUM suite. Measurement models using for least squares problems can be formed using the provisions of one of the existing GUM documents concerned with multivariate quantities. I won't give you extreme detail on this. I'll give you the thrust of the idea. Consider a set of data pairs which represent data points x and y. And perhaps we have covariance matrices associated with the x values, Vx, and associated with the y values, Vy. We want to model the data, fit the data by a function, y equals big F of x and p, where p is a vector of adjustable parameters. So we want to minimize an objective function, S of p, the objective function at the top of the screen, And so it's the sum of the squares modified by the covariance matrix of the responses, where E equals the difference between the function and the y's. At the minimum, F represents the data as closely as possible, given the measure S. To find a minimum, we do the usual thing. We equate to 0 the partial derivatives of S with respect to P. We have a set of n equations in unknowns, which define the estimates, and we solve by Newton's method or some such method. For the simplest case, we have an explicit multivariate model, y is a function of x and p. We can apply the provisions of GUM8 to provide the covariance matrix VP. So it's a simple covariance propagation formula to compute VP in terms of Vy, the covariance matrix associated with the y values, where the C's are the sensitivity matrix of partial derivatives of f with respect to y. So again, the idea of using the complex step method comes in to advantage. If we have errors in variables of regression, that means errors in variables is a common term to express the fact we've got errors associated with x values and errors associated with the y values. We can go through a similar process, but we need to introduce some additional unknowns. But again, we can produce at the end of the day, we can produce the covariance matrix associated with P by the use of foot points. And I won't give you an explanation of that, but we need those extra variables to formulate the problem. And so in this case, and sometimes in the case where we only have errors associated with the y values, we have an implicit multivariate measurement model, h of y, x, and p equals 0. Again, we can apply the provision GUM8 to estimate p and x star, which are the foot points in the previous diagram. Again, use Newton's method and apply a formula in GUM8 to provide the covariance matrix associated with the solution P. This approach is fully based on measurement models and output quantities. As I say, it's a mandatory feature of the GUM suite and fully consistent with the legacy GUM. By the way, the provided covariance matrix for the solution parameters is identical to that provided by the full Hessian matrix rather than J transpose J, J being the Jacobian as used in some approaches. So we get a complete solution within the provinces of what we're doing. We use hybrid measurement models at MPL quite a lot, where we know a physical model, we have knowledge of a physical model, but the physical model isn't quite right. We have an instance of tungsten filament lamps. Light emission from the lamp approximates that of a black body. A real lamp doesn't act precisely as a black body, but it acts something like a black body. The spectral irradiance of a black body source is modeled using the expression given in the middle of the screen. That's a basic theoretical model. But we have to adapt that basic model by an empirical term. The empirical term we use is a polynomial in lambda, wavelength, and temperature T. And so it's a product, the model we use is a product of a black body model and an empirical polynomial model. And we regard the empirical term as a correction function and with adjustable parameters, and we want to choose the number of parameters in that empirical model to give us the best fit to the data we're using. Here's an instance. This is the spectral response of a particular lamp, and the left-hand picture gives data point denoted by x's and the fit to that data by least squares, taking uncertainties into account, by a blackbody function. So that's the fit isn't good enough for our purposes, and so we adapt the model by the empirical function I mentioned. And on the right-hand picture is a degree 10 Planck polynomial model, the product of a blackbody function and an empirical polynomial function. The best degree was 10, selected using information criteria and taking account of the root mean square residual from a set of candidate degrees 1, 2, 3, etc. And so 10 is the best degree according to those criterion. If we're prepared to accept a somewhat larger uncertainty in the result, we can, of course, decrease the degree of the polynomial. In this case, we chose for our work at MPL the best degree selected according to the criteria. Monte Carlo. I mentioned the use of Monte Carlo already. GUM7 is a heavily used guide which presents the main principles in the univariate case where we only have one output quantity, and we sample from the input PDFs, we evaluate the measurement model of those samples, sample of the output quantity in the multivariate case automatically conveys the covariance information, which is good. It's needed for many purposes. For example, when we have a multi-stage measurement model and we're passing from one stage to the next. Is the Monte Carlo approach valid or not? The JCGEM, as I said, regards Monte Carlo as a gold standard. The size of the input sample is the only thing we have to control. It controls the quality of the output. As we increase the sizes of the input samples, we tend to have a better output. Asymptotically would have the true PDF, but what could go wrong? Look at the measurement model in the middle of the screen. Y equals x1 divided by x2, where x2 is a normal, characterized by a normal distribution function, normal probability density function. And the problem is the normal has infinite support to negative values and positive values. And so even if the uncertainty is small and x2 is removed from the origin, there's a possibility we'll draw physically infeasible values where the quantity is meant to be positive. But normality is assumed often when doing uncertainty calculation. When such values, extreme values, are possible, we shouldn't use such a PDF, but it's common practice. We want to know whether the Monte Carlo solution is going to be valid in such circumstances. For this model, with normal x1 and x2, the means and variances of y do not exist. In a particular case is where the standard normal distributions. The Cauchy distribution is the distribution which covers the output quantity y. It's more complicated otherwise, but we could be in trouble. The chance of such a value, in fact, increases with the size of the Monte Carlo sample. I said, as we increase the size of the Monte Carlo sample, we generally expect to get a better solution. But if we're going to have one of these extreme values, no. The difficulty is avoided when CV, U of x2 divided by the magnitude of x2, coefficient of variation, is small enough. Then y can be well approximated by a normal PDF with finite mean and variance. If we apply extreme value theory principles for a CV of 1/8, the probability is less than 10 to the minus 6 of a large Monte Carlo sample of size 10 to the 9, including a value more than 8 standard deviations to the mean. So that's a rule of thumb to suggest when Monte Carlo is likely to be valid even in these extreme circumstances. I'd like to finish with a discussion of the consensus mean, which applies in many problems. Suppose we're given a set of values which come from, in general, different distributions. And we want to find a consensus value, and we want to find the standard uncertainty associated with that value. Superficially, it's simple. It relates in particular to international work on key comparisons. The NMIs report their measurements, xi, of a circulated artifact with standard uncertainties U of xi. We require a consensus value, xref, and its standard uncertainty U of xref, and further derive statistics. Weighted mean based values methods are traditionally used. I give the formula in the middle of the screen, well-known formula. Metrologists have adapted these formulae to the circumstances. BIPM Directors Advisory Group, which I chair and have sat on since 2001, advises on such situations. It's a consideration for developing GUM9 in the GUM suite concerned with interlaboratory comparisons. There's a CIPM mutual recognition arrangement, which has been signed by over 100 NMIs 26 years ago. Within the MRA, NMIs publish statements of their comparisons and measurement capabilities. Data is available in the key comparison database. There are over 1,200 key comparisons recorded there. It's an essential reference for NMIs, etc. And from once we compute a reference value, a consensus value, we can obtain the degrees of equivalence as the difference between these values and the reference, and we could compute expanded uncertainties as well. And we have what we call CMC claims, comparisons and measurement capability claims, and these claims must be compatible with the results of key comparisons. I did a survey of 100 key comparisons taken more or less at random from the key comparison database. I found 50% exhibited inconsistency. And so I can reasonably assume that about half of the 1,200 key comparisons in all exhibit some form of inconsistency. What do I mean by inconsistency? Look at the picture on the right. I have the laboratories 1 to 10 along the bottom. The measured values provided by the laboratories are given on the vertical scale by the small circles, and the error bars relate to plus or minus 1 standard uncertainty about the central value. How do we deal with such data? Do we delete the data which appears to be discordant, such as laboratory number 10's value, the extreme right bottom corner? Do we inflate the reported uncertainties in some way, collectively or individually? It's a technical challenging problem, and there are politics entering the scene. A popular method used by NIST, used by PTB, and some other NMIs inflate all reported variances multiplicatively by the same amount. No, additively by the same amount. We call this excess variance. And we expand the quoted variances by just enough to give consistency according to a chi-squared measure. And yes, we can do this. Here's the data. This is data from this decision tree paper by Posolo in 2021. This is the same data I exhibited on a previous slide. And if we apply the excess variance method to all the laboratory results available, here in black, we have the same picture in black, and I've augmented that picture by an excess variance solution. And so you see each case has been expanded by the same variance. And so looking at this chart, we can see that they've all been expanded in such a way that the expanded uncertainty bars are comparable in size, which to me doesn't seem satisfactory. In other words, we regard all laboratories in the same way. Compare with this method. This method is discriminatory in that it has a separate excess variance for each quantity under consideration. I won't have time to give you the details, but I think it's a very promising method. I presented it to the BIPM Directors Advisory Group in the presence of the BIPM Director, who liked it very much. And so, as I said, I won't have time to talk about this now, but watch this space. It might be the future of key comparison data evaluation. I'll conclude. The GUM, now the GUM suite, has come a long way. It's still evolving, with new guides being developed. I've spoken about the past, present, and future of the GUM suite. I've mentioned some principles and tools I've found valuable in applications, complex step method, least squares approaches, hybrid models, and so on. I've emphasized validity or fitness for purpose. My main message is beware following the GUM blindly, assuming it will always work for you. Remember, you are in the loop. If in doubt, use Monte Carlo, which will nearly always provide a good solution, and we have a mechanism to identify when it's not doing well for you. Thank you.
Thank you, Maurice. Great talk. That's a very funny cartoon. Thank you. Thanks for sharing it. And thank you also for this great overview of the past, present, and future of the GUM suite and your advice, especially in the last slide. We appreciate that very much, and I hope people here will follow your advice. We have time for questions. Preguntas, comentarios. Jesus.
Maurice, thank you very much for your talk. My main question is that with over 30 years of the GUM, which software would you recommend to do all the calculations that usually we face in the academia and the industry?
I'm sorry, I missed the first part of your last sentence.
Which software would you recommend, either publicly published or commercially available?
That's a very difficult one because we've surveyed the scene. There are about 30 to 40 software implementations of the GUM. And I hesitate to, I can't wear a JCGEM hat in promoting a particular piece of software. But there's good software. I'm not going to say any more because I don't want to put my big foot in it.
Okay. Let me ask you another question. We are teaching newcomers to the GUM. We are teaching the GUM. Would you recommend to teach the GUM? Would you recommend to teach the GUM and Monte Carlo at the same time in order to make them more aware of the limitations of the GUM?
It's interesting because I started applying in my work on uncertainty evaluation. I've been involved with it for many, many years. I started off by applying Monte Carlo. It's like the difference between frequentist and Bayesian thinking. A lot of people are taught frequentist statistics at university. It would be much better they started with Bayesian methods. And I think Monte Carlo is a good start. And I'll certainly teach Monte Carlo alongside the GUM method, law of propagation of uncertainty, and so on.
Thank you, Maurice.
Thanks. Si quieren hacer una pregunta en español, podemos tratar de traducirla para que no tengan esa timidez. ¿Alguna otra pregunta o comentario? No? Maurice, I have one question or comment.
Yes.
As you know, I'm a Bayesian statistician. So I'm particularly interested in the draft of the that supplement that it's going to talk about the Bayesian methods. I think it's a long way in the working, so I would like to know if there is any idea when it's going to be published, or how much work is it necessary for it to be published?
Well, there's quite a lot of work to be done, but it's lower in the list of JCGEM priorities than it should be. We want to complete the guide that I mentioned, the containing lots of examples. We want to complete that, and the revision of the Monte Carlo guide is underway. I'm responsible for that, and so we want to complete those first. But we have some ideas, and informally, I might be able to provide you something, Eduardo, in the near future, but it's for your personal attention.
Okay. Well, thank you.
Yes.
We have a lot of young people here, so I would like to ask you what kind of advice would you give to them, to this new generation, and not only to mathematicians, but also to young students from other areas, chemistry, physics. So what kind of advice could you give them?
Advice in approaches to uncertainty evaluation you're talking about?
Yes.
Well, I can only repeat, Monte Carlo is the gold standard. It's recognized as the gold standard by the JCGEM. And I'd like to see attention paid to that. And I'd certainly teach the Monte Carlo because it's quite a straightforward concept. You assume the probability distribution of the input quantity. And there's a lot of talk about how do you provide those PDFs? How do you provide them? Sorry, I had a phone call. I switched it off. And expert judgment is an important consideration. I would like to see more attention paid to elicitation, whereby you ask the practitioner what he knows about the measurement, and ask him such questions as, do you expect the value you're interested in to lie between certain limits? If so, what do you expect those limits to be? Can you say anything about the median expected value?
Right.
And so on. And gradually homing in to giving information, and to that information you fit the simplest distribution that satisfies that information, and feed it back to him and say, is that suitable for your purpose?
Great.
Elicitation is often done with a panel of experts, but often you only have the opportunity to work with one individual. And elicitation is a method that is really firmly supported by Tony Hagen, by my Bayesian colleague at Sheffield University, already mentioned. And so I'd like to see that taught more strongly.
Okay, thank you. You're talking like a Bayesian. I like that. That's a Bayesian argument. Thank you very much.
I'm not an expert Bayesian, but I like the Bayesian way of thinking.
Okay, thank you. Okay, I think we are on time. We're finished. We once again thank you for your presentation, for your input, for your talk, and we hope to see you soon somewhere. Thank you very much.
I hope so.
Please
Right.
give our regards
Pleasure.
to Janet.
Yes, thank you, Eduardo. Thank you, Jesus. Bye-bye.
Maurice, thank you very much, and I hope we will see you again in Mexico.
That will be good. Right, bye-bye.